Hi everybody, sorry that I am not there today. I did not expect to be out, so here we go. I'm going to do the best we can. So we're moving into some of the rules now to find the derivative. So far we've used the definition of the derivative, and as we observed, some of them you saw patterns for, and others it was a whole lot of work to end up with like a simple answer like 7x or something like that. So there are some rules that you can use from those patterns that help us. So the two we're going to talk about today are the constant and power rules. The constant one is very easy. So quickly, we have this little chunk here. This is just reminding you that you're going to see it different ways. We're still talking about the derivative either way, but when you see it as dy dx or f prime of x, that means it as a noun. Like this is what the derivative is. If you see d over dx, it's telling you to do something. So take the derivative, actually calculate and figure this out. So with the constant, if you have a constant number, the derivative is going to be 0, just flat out, that's it. So if all of these, dy over dx would equal 0. Here, the derivative of x is 0. Here, the derivative of t is 0. They're all the same. Now, see how it says k is a constant? That matters because when you multiply two numbers, you're going to get another constant. So even though it looks like you have two things going there, it's still just multiplication. So again, my notation would be dy over dx is equal to 0. All of them were 0 because they were all constants. Easy enough. We're not going to say much more about that. Okay, the power rule. This is the one we talked about a couple weeks ago when we were just trying to quickly get the derivatives. So the explanation up top might look a little bit wild, but when we have some function where it's a constant times a variable to a power, the derivative, when you take the derivative of that function, is going to be the exponent multiplied by the constant coefficient, so a times n, and then the variable to that number minus 1. So if you had, for example, I'm just going to put an additional example up here. If I had f of x equals 3x squared plus 2x, 2 times 3 is, so this is the derivative of x. 2 times 3 is 6. X to the 2 minus 1 is 1. Plus, this is technically an exponent of 1. 1 times 2 is 2. 1 minus 1 is 0, so x to the 0 would just be 1, so we would be left with that. Okay. We're going to use this power rule all over the place today. So here we go. For this first example, so the derivative of x would be my notation. Again, exponent times the coefficient, so 3 times 2 is 6. Variable, and then the exponent decreases by 1. So that's it. My derivative's done. Instead of doing that entire definition of the derivative like we've been doing, we can just be done there. Okay, I'm just going to draw a line here to separate the two. With a radical, with any sort of a radical, you need to remember your power over root simplification. So anytime you have any sort of root, that's actually an exponent. It's a fractional exponent. So first I would rewrite g of x before doing anything further as x to the 1/3 over 3, because again, this is, we always said power over root 1 over 3 is how I got that fraction. Okay. Now, furthermore, this divided by 3, I can actually rewrite as a coefficient of 1/3. And now that I have it rewritten as such, I can take the derivative by multiplying 1/3 times 1/3 and getting 1/9. And then x to the 1/3 minus 1 would be negative 2/3. And that would be my derivative. If I wanted to clean that up even further, I would write it as x. Oh, no, I would not put x on the top because I have a negative exponent. I would write it as 1 over 9 x to the positive 2/3 because a negative exponent actually comes down to the bottom. Okay, this next one, using that same concept, I'm going to rewrite y as 5/3 times x to the negative pi. I have x on the bottom there. If I want to bring it to the top, I make it a negative exponent. Now I can calculate the derivative of y, which should be written as dy over dx negative pi times 5/3 is negative 5/3 pi. And then it would be x to the negative pi minus 1. That one I wouldn't try to do anything fancy with and rewrite it on the bottom. I would just leave it like that. Okay, now we're going to put all of that together. So I'm going to rewrite y as 6 to the x to the negative 3/5. Again, negative because my x was on the bottom of the fraction. And then 3/5 because power over root. So then when I find the derivative, I get negative 3/5 times 6, that's negative 18/5. X to the negative 3/5 minus 1 would be negative 8/5. That's negative 8 over 5. I know it, my handwriting is getting tiny. Sorry, I'm using my finger on this thing. And then I could rewrite that as dy over dx is equal to negative 18 over 5x to the 8/5. And that would just be the cleaned up version. Okay, so we're just going to do a bunch of those examples today. I'm going to do a couple, then so in these first 4 examples, we're just doing the basic power multiplying and then going down by 1. So because I have y here, my form would be dy dx. 4 times 5 is 20, and then it would be x to the 3rd because I take my exponent and go down by 1. For number 2, I have dy dx, and 4 times 3 is 12, x to the 3rd because it goes down by 1, plus 3 times 3 is 9, again the exponent goes down by 1, plus 4x because the exponent went down by 1. If you want to write x to the 1, that's absolutely fine. So at this point, you should pause it and do 3 and 4. I'm going to show you the answers to 3 and 4 on the next slide, but again, please pause first and try 3 and 4 on your own. Here are the answers to 3 and 4. Hopefully you tried them first. If you didn't, try them and make sure you get the right answer. Okay, number 5, it's just with negative exponents now. It works the same way. So dy dx is equal to, that's going to be positive 5x to the negative 2. And then this is going to be plus 3x to the negative 4, again, because you decrease by 1, so that negative goes down by 1. And then if I wanted to clean this up, to have all positive exponents, this would be 5 over x squared plus 3 over x to the 4th because of my negative exponent rules. Go ahead and try 6, 7, and 8 now. The next slide is going to have the answer to them. Again, hopefully you tried them first, but there are your answers. Okay, now there's lots of rewriting when you want to do the power rule, because the power rule only works when it's in that form of like something plus something plus something. You can't use it otherwise. So that is why we do all of this rewriting at the beginning. So I'm going to rewrite this as negative 3x to the negative 5th, and now I'm back to what we were doing before. So the derivative of x is positive 15x to the negative 6, which cleans up to 15 over x to the 6th. On the right here with number 10, again, I'm going to rewrite it first. So 4x to the negative 1 minus 5x to the negative 3 minus 1x to the negative 4. I didn't really have to write the 1, but I was on a roll. So my derivative, negative 1 times 4 is negative 4x to the negative 2 because I'm going down 1. This is positive 15 x to the negative 4. And then this is positive 4x to the negative 5. And finally, I just clean it up. And I have negative 4 over x squared plus 15 over x to the 4th plus 4 over x to the 5th. And you're seeing why all those exponent rules and all the different algebraic things you learned up till now, really, this is where they... Here are the answers to 11 and 12. I don't know why I wrote them twice, but you have a big version and a small version. There you go. 11 and 12 are there for you. Please do them first and then verify that you have the right answers. Okay, moving on to 13 and 14. Now we have fractional exponents. Again, it still works the same way. If you're not comfortable multiplying fractions, grab a calculator and let it help you. So the derivative in this case would be 4/5 x Now 2/5 minus 1 would be negative 3/5. So then I could clean that up and get 4/5x to the 3/5. Just like that. Okay, 14, again, I'm going to use the power rule. As such, I will get negative 10/2, which is 5. X to the, when I subtract 1 from that, I get 3/2 plus 2/5 x to the negative 4/5 when I subtract 1. I'm still just doing that same pattern. Yeah, it might take a little bit more time because it's fractions. Okay, so this is now going to be negative 5x to the 3/2 plus 2/5x to the 4/5. Okay. So we're just continuing that pattern, but there's lots of rules with those negative exponents that you got to remember. And I get that might take a while. So now you should try 15 and 16, and as before, the answers will be on the next slide. And there they are. 17 and 18. Now we're just dealing with a bunch more variables, but remember 2 times c is still some number c that's a constant. In that case, that means that whole number is a constant, so the power rule still applies. So I'm going to start by rewriting f of x. X is to the 2/3 because again power over root, plus 2 times x to the 1/3 again because of power over root. And now I'm going to calculate the derivative. 2/3 times 2 is 4/3. Cx to the negative 1/3 plus, notice that the x is the only thing actually being raised to an exponent, right? If you think about your order of operations, that's important to note. So 2/3 x to the negative 2/3, because again, I'm subtracting 1 every time. And now I clean that up for my final answer. And that is 4/3 c over x to the 1/3 because of the negative exponent, plus 2/3. Oh, I just realized I could have made that better on the other one. I'm going to fix it. 2/3x to the positive 2/3. And over on the left side, I could have 4 and c stay on the top, and then 3 could go on the bottom. It's equivalent to what I had written down. It's just prettier this way, so I'm just rewriting it. Okay, moving on to 18. Again, I'm going to rewrite as step 1. Anytime I rewrite, notice that I'm telling you that it's the same, it's equivalent as the original function. I'm just rewriting it. So negative a x to the 2/5 minus 4b x to the 1/5 minus x to the 2/3. Now I'm actually calculating the derivative based on my notation. So negative 2/5 a x to the negative 3/5 minus 4/5 b x to the negative 4/5 minus 2, I can barely fit it, 2/3 x to the negative 1/3. Again, that last one is minus 2/3 x to the negative 1/3. So then when I clean it up, I really am trying to write clearly, I swear, equals, so I have negative 2 and a on the top over 5 x to the, I'm moving that to the bottom by changing it to a positive exponent, minus 4b over 5x to the positive 4/5 minus 2/3x to the 1/3. So that would be my final answer there. Okay, again, try 19 and 20. Answers are coming up in the next slide. And the last two I'm going to do with 1 and 22. And this is just dealing with a lot of exponents. Again, this is just reinforcing that rule. So when we calculate the derivative, we always multiply the exponent by the coefficient. So 2a times 2 is 4a. And then we raise the exponent to the exponent minus 1. So this is how your final answer would look. So 5bx to the 5b minus 1 and then plus 2bx to the 2b minus 1. That would be your final answer for 21. It's just looking for it in that notation. For 22, the derivative of x is equal to negative 6b x to the 2b minus 1. You're essentially just writing out that pattern. Okay, so 23 and 24, I think, are your last two. I may have only accidentally copied the answer to 23. If so, 24 will be a surprise, and you can check that tomorrow. I'm not going to re-record just to paste that one answer. Here's the answer to 23. I forgot to copy the answer to 24, sorry, but I will do that. Like I said, we can just go over that tomorrow. Any questions you have, we will go over tomorrow. Again, sorry I wasn't there, and I hope you have a wonderful day. See you later. Bye.